of course. So, again, hello everyone, wherever you are in the world. I am Gianvito Scaringi, and yeah, today I'm going to present a work and its background. Actually, it's a work that was presented in that was published in Geomorphology. I work at Charles University in the Czech Republic. And I am there an assistant professor, but I'm actually from Italy, and where I did my master and my PhD in geotechnical engineering. After that, after my PhD, I spent a period, a couple of years in China for a postdoc focusing on landslides, in particular on earthquake-induced landslides. In Prague, in Czech Republic, instead, my work is concerning more the thermal aspect of the behavior of the geomechanical, of the behavior of geomaterials. So I shall get started by saying that, and by acknowledging funding from the European Union for this project that involves me and Marco Loche, who is also from Italy and is a PhD student, almost finishing his PhD with me in Prague, Czech Republic. So why a thermo-hydro-mechanical approach to soil slope stability, and why this reference to climate change? Let's try to understand with a bit of background. First of all, why thermal geomechanics? Now, why this subject? I advocate for establishing thermal geomechanics, so thermal soil mechanics, thermal rock mechanics, as a specific branch, a specific direction of research, and if you want, even a specific subject to teach at university, by collecting and structuring in an organic way, this is my work now, all problems that can occur in nature or in engineering, in which the knowledge of temperature dependent or thermally activated processes is crucial. And in fact, there are many applications, some that are in a bit more advanced stage, and some other are just starting to appear in the literature. One of the applications which are more advanced in terms of development is the use of thermal geomechanics in deep geological repositories of radioactive waste. But also there are applications in geothermal piles or in shallow geothermal pumps in general. And then, that's what I'm trying to develop more, in the study of the stability of slopes in various climates, in various conditions. So from rock slopes at high elevation that are threatened by ice melting, down to more gentle slopes and the hill slopes that can be overheated by wildfire, in terms of very shallow cover, or progressively over a long time by global warming. My paper, our paper in Geomorphology, is a review paper, so that's why I'm talking more about the work done by others to set a scene, to set a starting point for my own research and for future research. And in fact, progress in science is often made because there is some need, because a need arises, and this need is often very practical. There are very practical motivations that trigger certain studies, and the first studies on thermo-hydro-mechanical, THM, behavior of geomaterials in engineering or engineering geology date back to the 1960s. A pioneering report commissioned by the US Highway Research Board was prepared that time by Professor Jim Mitchell, that I think many of us know for his achievement and for his handbook, Fundamentals of Soil Behavior. He collected and discussed 14 papers in the 60s, focusing on various aspects of temperature and heat effects on the mechanical properties of soils. In his case, there was a practical issues in transportation, in geotechnical engineering in transportation, because the newly built soil road embankments in very arid and hot areas in the west of the United States would get damaged, and so they would try to understand whether this damage of this embankment was caused by the extreme variation in temperature during day and night or over the season. So this was really a pioneering report, and it collected really interesting insights on the thermo-hydro-mechanical behavior of soils in particular. So one of these studies that I like particularly shows how a normally consolidated clay, in this case it's a remolded sample of illite, can shrink when it's heated during consolidation. These are it's a consolidation phase of a sample. The material was normally consolidated, I think, down to 200 kilopascal, then maintaining the stresses constant. Simply, it was heated, it was warmed up from 18 to 59 degrees and then down and up and down again. So the soil would shrink upon heating and swell upon cooling, even though this may seem counterintuitive. And the process was repeated cyclically, and it was shown to be partly plastic, so with the irrecoverable deformation at the beginning in the first cycle, and then it turned out to be fully elastic. But what is interesting is that by heating and cooling a clay soils, you could obtain an overconsolidation, and apparently it's not a real overconsolidation in mechanical terms, but the volumetric response is exactly that. Heating and cooling would cause the same shrinkage, the same consolidation that could be caused by a loading-unloading cycles. And of course, upon further loading, this would result in stiffening. So the material, which is heated and cooled, would settle and become very stiff at a certain point, that you need a much larger load to produce other deformation. So by heating and cooling a material, you can actually get some benefits in terms of mechanical response. There is also a corollary to this, because if you sample a soil in the field and you find out that it's overconsolidated, let's say that the overconsolidation ratio of a soil that you sample in the field is 2. Now, this overconsolidation, you would think that it's because of a mechanical overconsolidation, but that is not sure. An overconsolidation of 2 could have been obtained simply by heating and cooling, by natural heating and cooling of a normally consolidated soil. So that tells you that even when you think you have the answer, maybe that answer is not mechanical, maybe it's thermal. Now, broadening a little bit and focusing in particular on saturated soil, in general, thermally induced volume changes depend on two things, basically. They depend on the different thermal expansion coefficient of the minerals composing the aggregates, let's say, in the soil, and water. Typically, the thermal expansion of water is way larger, it's way greater than that of the individual mineral. But that depends, that effect depends on whether the soil has an open structure or a closed structure, because if the soil has an open structure and the water is expanding in the pore, maybe these aggregates that are in contact, they may lose contact, they may detach, and so that you can have a collapse. So that's why in a normally consolidated material, when you heat the water expands and the structure actually collapses and the water is expelled. But particularly in clay, there is also another effect that is related to the physico-chemical interaction on the clay mineral surfaces. So it's a microstructural effect. And this microstructural effect in clays is actually what typically dominates the entire thermal sensitivity of a clay-rich soil. And that happens because the water absorption capacity of clay minerals is really strongly influenced by temperature, and the roots are in the chemistry, in the thermodynamics of the microscopic processes. It's there that really a lot can change in terms of chemical bonds, hydrogen bonds, because these bonds can get broken at high temperature, can get stretched, and water can escape from the surface of the clays that can actually dehydrate at high temperature, again shrinking the entire microstructure. Now, this picture, this volume change behavior, so that described this way phenomenologically in the 60s, actually is valid if we assume fully drained condition. But if the change in temperature is rapid compared to the ability of the soil to deform volumetrically by expelling or sucking up water. So it's actually a competition between the thermal forcing and the hydraulic conductivity of the soil. Well, the response to thermal forcing may be undrained, or at least partially undrained. And if the response is undrained, what we get is a thermal pressurization. If we are heating a normally consolidated soil, the soil wants to shrink, but the permeability is really low. Well, we have a time in which there are high pore water pressure, and we get consolidation, exactly like a hydromechanical consolidation, because of the progressive dissipation of pore water pressure excess. This pressurization is larger if the material is stiffer. So you see this on this MV and MW. These are compressibility, volumetric compressibility of the water and the solid skeleton, and the smaller is the compressibility, the larger will be the pore water pressure response. It can be calculated that a change in undrained condition of just 1 degree Celsius can cause a change in pore water pressure in the order of 1.5%. Now, this seems tiny if seen like that, but now consider a situation in which you have already an active landslide. Consider a slow-moving, creeping landslide that is moving continuously, and maybe it has a seasonal acceleration. This landslide has a factor of safety that is basically 1 or very close to 1, or it gets 1 when there is a remobilization, a fast period. This is a case study that it actually does not involve temperature. It involves changes in pore water pressure, but I show this as an analogy. So think that in this case of a clay landslide, we have seasonal changes in pore water pressure. This is deep-seated, so it's deep pore water pressure. They don't change much because of the surface rainfall if there are no discontinuities that really communicate hydraulically with the shear zone. But anyway, you have changes in pore water pressure in this case study in the order of 3% between summer and winter, between rainy and dry season. This 3% causes changes in safety factor in the order of 3%, but in terms of movement, these are deep displacement evaluated with inclinometer. You have accelerations during the active season of the landslide by 1 order of magnitude or more, meaning that a 3% loss in factor of safety makes the landslide 10 times faster. Now consider that a 3% decrease in safety factor can be caused also just by an increase in temperature of 2 degrees. And 2 degrees warming at a certain depth in the underground is very likely between summer and winter. So you can consider that there might be in the world landslides that are remobilized or accelerate because the ground is getting warmer and the soil is weakening, or it's pressurizing. No? Of course, this is hypothetical, but as a mechanism, it's perfectly possible. 2 degrees change over the season in a very low permeability material, it's actually partially undrained, because in a very low permeability clay, it may take years to dissipate pore water pressure excess. So it's perfectly reasonable. Now, this is a mechanism that actually involves volumetrically induced thermopressurization, let's say. But besides that, experiments show a direct thermo-mechanical mechanism, sorry for the wordplay, which occurs also in drain condition. And most publications available now in the literature indicate generically a decrease in strength with temperature increasing. So warmer temperature make the soil weaker and more prone to landsliding, more prone to reactivation as well. But the actual situation, to say, it's a bit or maybe a lot more complicated than this. And in fact, if we just take the peak shear strength, this is a very nice work again from the 60s, from that famous report. The peak shear strength is influenced both by the temperature during shearing and the temperature during consolidation. So you can get a pronounced peak with a post-peak decay also in soil that are consolidated at high temperature, but then they are sheared at low temperature. Imagine a soil that is subject to hot summer temperatures, and then it fails as a landslide during the winter. The behavior will be strongly like an over-consolidated material, in fact, exhibiting a high peak and a post-peak softening. And that's because of the different thermal condition during consolidation and shearing. But in general, if you look at the picture, on the horizontal axis, you have the reciprocal of the absolute temperature. Here you can get the actual temperature, on the right, low temperature, on the left, high temperature. And these lines, they are sloping towards the left, meaning that at a given temperature of consolidation, the peak strength decreases with increasing temperature of shearing. So if you have a consolidation at a certain temperature, no matter what, if shearing or if failure occurs at higher temperature, the peak will be lower. So actually failure should be easier. Very interesting result, but let's move on from the peak to the post-peak to the residual shear strength. This is a much newer study, just a few years old, which we actually dissected, and we are repeating certain experiments to understand whether there is really a strong pattern, if they are repeatable on many materials. This group of scholars from Kyoto University, in fact, they published in Geophysical Research Letters and in JGR, the AGU journals, evaluated the residual shear strength of a natural clay on the left. This is a natural clay containing smectite, and on the right, they used a commercial calcium bentonite to better evaluate the behavior on a pure material. They made ring shear tests at different temperature. In particular, black line here shows tests conducted at room temperature, 20 degrees, 22 degrees in their case. They did it when it was warm in the lab. But then they cool down all the experiment. Normally, you cool down the water bath that is saturating and the circulating bath that it's around, that surrounds the samples, and in this way you cool down also the sample that is inside. They cooled it down to +7 degrees Celsius. They did not freeze the soil. They just cooled it down to simulate autumn conditions, for example, in the slopes of this area in Japan. And what they noticed was an over 10–15% decrease in the shear strength, over 1 degree loss in residual friction angle, that for a slope that is already unstable really can make a big difference, can remobilize, can speed up an existing landslide. They did the same for a commercial soil. They also went into warming, and they say that the colder is the temperature, the weaker is the material in terms of residual shear strength. But however, this thermal sensitivity, which is very large here, it depends very much on the type of material that we are testing. It depends on the mineralogy of the clay component, because it's something that concerns the physico-chemical interaction in the microstructure. And in fact, the same scholars analyzed a large number of soils, of clay soils in particular. We see a very wide range of liquid limits and plasticity index in this classification chart. And these are the results that they obtain in terms of effect of temperature on the strength. They call positive effect an effect that is consistent in sign. High temperature, high strength; low temperature, low strength. They call negative an effect that it's reversed, that it's inconsistent with that, so meaning that strengthening upon cooling, weakening upon heating. And they noticed that the more smectite, the lower the friction angle the material had, the stronger was this cooling-induced weakening. And the magnitude of these effects is very similar to the magnitude of thermal pressurization, actually, 1.5% per degree, suggesting that probably the phenomenon has the same physico-chemical root. Interestingly, this pattern is only valid for slow shearing, the typical slow shearing that is done in the laboratory. If the soil is sheared fast, and fast I mean above 0.1 millimeters per minute, which in terms of landslide movement corresponds to rapid landsliding, the behavior is reversed, and smectitic clays weaken at high temperature, which is something more known in the literature for fast landslides. In fact, we in our laboratory are exploring whether on the opposite side, non-smectitic clays, for example, kaolinite, would actually strengthen at fast speed, and it seems that it is like that. The author in these publications used also a classic approach, which dates back to the studies of Tika Lemos and Peter Vaughan at the Imperial College in the 90s, to explain this temperature and shear rate dependent coupling in terms of weakening or strengthening with the prevailing mechanism of shearing, the mode of shearing, they call it, in the shear zone. And just to be complete, moving from the residual strength to creep, which can be volumetric but also shear creep and its dual, stress relaxation, we find from the literature that both of them depend on temperature. And again, we are going in our laboratory to make tests on that, doing a shear creep test in direct shear devices. And key to understand why creep depends on temperature, we need to look again at the microstructure, at the interparticle bonds and the chemical bonds, how they are broken at higher temperature with more ease. And there is consensus that at elevated temperature, creep is more likely and is faster, but relaxation is more rapid. Now, after this big overview of the literature, why I told you all this? Well, because in the field, the temperature of the slope is not the same across the world, first of all. It's not the same with depth. It's not the same over time. Temperature changes continuously in the slopes, especially in the shell of 5 to 10 meters of underground. Temperature is continually varying. And it's also changing over time, over a long term, again, I mean decades, century, because of climate change. And for example, in this figure, there are thermal patterns which are calculated just with heat diffusion equations, very simply in GeoSlope software, that summer, autumn, winter, spring season have different patterns of temperature in the underground. In particular, you have a thermal inversion layer in winter where you have a lens of soil that is actually warmer at a depth that can be 5, 10 meters, because it is the heat wave that is propagating from the summer, and it takes several months to reach that depth before it fully dissipates and before a new wave comes because of the new spring and new summer. So the pattern, it can be even irregular, it's non-monotonic. But now think of having a slip surface, a landslide in this slope. Clearly, the slip surface is crossing layers of soils at different temperature. So even if the soil is completely homogeneous in terms of other properties, and you want to do an analysis considering a homogeneous soil, well, that soil is not homogeneous with respect of temperature. It has patterns in it. And as a result, especially if that soil contains clay, at different depth, you will have a different peak strength, different residual strength. And we can argue that the safety factor, we are doing this analysis in these days, the safety factor over the seasons and in time, because of climate change, can really change a lot, can change by 10, 20, 30%, depending on the areas of the world and the depth of the slip surface. So it's not something that should be simply neglected. It has to be calculated. That's why I advocate for a thermo-hydro-mechanical approach to soil slope stability. We need to include temperature in this model to increase the accuracy of this model. I can even argue, but this now is speculation, it's more for fun, that imagine you don't have a slip surface, but a landslide is going to happen soon, and the slip surface starts to form. If it forms in summer or in winter, maybe the slip surface will not be the same, will be more or less deep, because it will start to, a slip surface forms following weak layers, following weak material. And if the material is weaker at a certain depth, you might have, again, speculation, more deep-seated or more shallow landslide triggered in summer or in winter, just because of the different temperatures in the underground. From speculation, let's move, and I'm almost finishing, to actually a real case. This is the same case from these guys from Japan that actually found a real landslide that could be explained only because with changes in temperature. There were actually a group of landslides in active clays in a certain region in Japan, and they went to the field. They could not understand, why is this landslide moving? Well, there is no rain, no snow melting, nothing, no earthquakes, pore water pressures were not changing, yet every year the landslide would move in autumn, in late autumn, when the soil was actually cooling down. They took samples, they analyzed them in the laboratory, and they actually found out, and I showed you before, that from room temperature, while cooling down this material, the friction angle would decrease, and that is what could explain, the only thing that could explain this periodic landslide reactivation. I think it's a great case study. But beside these, and maybe a couple of more studies that suggest a similar phenomenon in the field, evidence is actually scarce. And I think we do not have evidence for two reasons. And one reason is that we are not searching for it. We are not looking for evidence because the models that we are using simply do not have temperature in it. So we will never be able to see thermal effects if our stability models, constitutive model, or even regional scale susceptibility model do not include temperature as a parameter, as a variable. You will never see it simply. And why you are not including it? Well, because traditionally hydromechanical approaches in slope stability work well enough. Of course, they have uncertainties, but so far we have accepted these uncertainties. But maybe these uncertainties are large, especially in some cases. Maybe 15, 20% uncertainty has become unacceptable. And we have to make a step further, use a more advanced model to actually find better answers. Same goes for regional scale analysis. We have a lot of studies using morphological, geological, hydrological, land cover variables. In some cases, susceptibility models use geotechnical variables, but very little cases, because typically geotechnical parameters over large areas are not available, or they can only be calculated based on the lithology. So it's not a new variable, it's not independent. And surprisingly, or maybe not so, over 600 landslide susceptibility studies, which were analyzed in this review paper by Paula Reichenbach in Earth Science Reviews in 2018, none of these 600 studies ever considered temperature in any way. Temperature of the soil surface, temperature in the underground, never. Even though, and that's interesting, surface temperature data are available. They are measured by satellite, so you could even readily try and input it in your susceptibility models. And we have done so, and it actually works. Before I move to that, this was one reason. The models do not include temperature. The second reason why there is not much field evidence is because the field is not as simple as the laboratory. In the laboratory, samples are homogeneous, are simple, you control the condition. But in the field, you have different lithologies, in fact, different type of landslides, and so different thermal effects. For example, this table that comes from our paper in Geomorphology shows the possible effects of temperature depending on the depth of the shear zone. So shallow versus deep-seated landslide, thermal effects are different. Thick or thin shear zones, effect is different. Planar or rotational landslides, clay or non-clay materials, initiation, triggering or run-out phase of landslide or remobilization, slow-moving versus fast landslide, normally consolidated versus over-consolidated landslide. We have analyzed all these aspects to try and understand the possibility of different thermal responses. So if you study an entire country and think of, okay, with climate change, the surface is going to be 10 degrees warmer. Are we going to have more or less landslide because of temperature? I mean, of course, because of weather, storms, you are going to have probably different patterns of landslide. But excluding that, just because the soil is warmer, the ground is warmer, are we going to have more or less landslide? Well, it's not easy to answer because of this large heterogeneity. So we have to make subsets, sub-regions, which are more homogeneous, and then perhaps we can say something. For example, let's only take slow-moving landslides in clays. We are doing this for the case study of Italy. We are in progress of publishing something that shows that in Italy, slow-moving clay landslides are actually affected systematically by temperature, and we can see these patterns statistically. But and this is my last slide, another successful case that we have already published in scientific reports is the following one. We took the inventory of landslides in the epicentral area of the Wenchuan earthquake in China. And this area is, of course, dominated by a single trigger, the earthquake, and a single lithology. There is a single lithology which is poor in clay minerals, actually. And we analyzed the patterns of remobilization of co-seismic landslide deposits for 10 years after these strong earthquakes. We compared it with the temperature of the slopes, the surface temperature of the slope that could tell you something also of the underground temperature, of the basal temperature of these landslides. What we found, quite interesting, was a good correlation with surface temperature and between surface temperature and the abundance of landslides on certain slopes. It was found that for this material that it's non-clay or non-active clay, so it's consistent with the laboratory analysis, warmer slopes meant more landslide, more remobilizations along those slopes. Quite interesting, but of course this is a statistical work, meaning that it can give insight, but correlation does not mean causation. So this requires an in-depth study. I wish to conclude by saying that this topic, this thermal geomechanics and this thermal slope stability seems quite promising, and I'm open to collaboration, of course, to develop modeling approach, and even more importantly, to find field evidence that would support these approaches in other parts of the world. And finally, I wish to thank you all again for listening, and Roberto for inviting me and for organizing this very nice online event. Thank you very much, Roberto. I'm of course open to questions.